Hello there, Mr. Sutton here, bringing you the BC Calculus 8.5 Part 1 homework solutions on polar functions, slope, and basic area. For this problem, we want the slope of the tangent line for the polar curve r equals 1 plus 2 sine of theta at theta equals 0. So in general, to get dy over dx for a polar curve, we need to do y prime of theta over x prime of theta, which means we need to express this in terms of x and y first. So for x, in general, we have x equals r cosine of theta. So in this case, we have 1 plus 2 sine of theta, all of that times the cosine of theta. And we're going to simplify this now just to make it a little easier to take the derivative. Otherwise, I'm dealing with the product rule right away. So distributing this, we've got cosine of theta and 2 sine cosine. Now this pattern here, 2 sine of theta, cosine of theta, we know that's equivalent to sine of 2 theta. So we're going to definitely use that double angle identity to make the next step a little easier. So now taking our derivative, for cosine, this is going to be negative sine of theta. For sine of 2 theta, this is going to be 2 cosine of 2 theta. So using a little chain rule, still better than using the product rule. And that's going to be just about it now for x prime until we have to plug something into it. So now let's figure out y. Y of theta, in general, is going to be r sine of theta. So we still have our radius again, 1 plus 2 sine of theta. This time we're multiplying it by the sine of theta. And let's distribute that out. So we have sine of theta plus 2 sine squared of theta. Taking our derivative here, because there's really no way to simplify this otherwise, we've got cosine of theta. And this is going to be another chain rule. So this is going to be 4 cosine of theta, or sine of theta rather, times the derivative of sine, which is cosine. There we go. Now, this is just twice what we had up here. So this is going to end up being 2 sine of 2 theta. So cosine of theta plus 2 sine of 2 theta. And now we're ready to go ahead and plug in 0. So in general, we're going to have y prime of 0 over x prime of 0 if I'm trying to evaluate the derivative, the dy over dx at theta equals 0. This is just our parametric derivative set up here. So y theta, or y prime of 0, that's going to be 0 plugged in here. So we have cosine of 0 plus 2 times sine of 2 times 0. And now x prime of 0, we're using x prime up here. So negative sine of 0 plus 2 cosine of 2 times 0. So we've got, let's see here, this is going to be 1 for cosine of 0. And let's see, this is essentially sine of 0, which is also 0. So we end up with 1 in the numerator. Down here, sine of 0 again is 0. This is cosine of 0, which is 1, but we have a 2 multiplier. So altogether 2 down there. So hey, 1/2. Choice B. For this no calculator problem, I want the slope of the tangent line for the polar curve y equals cosine of theta at theta equals pi over 6. So for polar slope, to do dy over dx, I need to express this parametrically as functions of x and y. Let me start with x and then I'll take its derivative. X in general is r cosine of theta. So in particular here then, our x of theta that we're coming up with is going to be this cosine of theta, which is the r value, times the cosine of theta that normally goes with this x value here. So if I've got cosine times cosine, I'm just going to write this as cosine squared of theta. So let me go ahead now and take the derivative of that, x prime of theta. Using my chain rule, that's going to be 2 times cosine of theta times the derivative of cosine, which is negative sine of theta. And I'm immediately going to clean that up because I know simpler is better when I'm doing these problems, especially without a calculator. So this is negative 2 sine cosine, which using my identity of 2 sine cosine equals sine of 2 theta, I can rewrite this as negative sine of 2 theta, using that double angle identity that I use so often on these. All right, now I need to write out my y of theta. That's going to be r sine of theta. So that's going to be cosine of theta, sine of theta. And I can also use this double angle identity on this one. This is going to end up being 1/2 sine of 2 theta, which is a little bit nicer to work with. So now let me take the derivative, and the benefit of doing this now is I avoid having to use the product rule when I do y prime. So this is just a simple chain rule. I've got, let's see, 1/2 cosine of 2 theta times a tail of 2. So this would just be cosine of 2 theta. All right, it's time to put this back together now in a slope formula. So I should have y prime of theta over x prime of theta. And if I'm evaluating things at theta equals pi over 6, these should both be pi over 6's here. There we go. All right, so y prime of pi over 6. Well, here's y prime. This is just going to be cosine of 2 times pi over 6. And then down here, x prime of pi over 6, that's going to be negative sine of 2 times pi over 6. So back up here, this is really, let's see, cosine of pi over 3, or 60 degrees. We know that to be 1/2. And here we have negative sine of 60, which is going to be negative radical 3 over 2. So using a little same change flip, I've got 1/2 times 2 over radical 3. 2's are canceling, so this is just going to be negative 1 over radical 3. Or you could just cancel these mini denominators. Either way, this is what it shakes out to, and that gives us answer choice B. For this problem, we want the slope of the line tangent to the curve, polar curve r equals 2 theta squared at theta equals pi. So basically, we need to take the dy over dx of this thing and then plug in pi for theta. To do this, we're going to need to express this parametrically in terms of x and y. So using x equals r cosine theta, I can write x equals 2 theta squared times cosine of theta. And now to take the derivative of this thing, I am going to need the product rule. So let me get the box and ribbon out here. So I've got 2 theta squared and cosine of theta as my factors. The derivatives are going to be, let's see, this is 4 theta, and this one is going to be negative sine of theta. Using the ribbon to put it back together, I've got 4 theta cosine of theta minus 2 theta squared sine of theta. And is there any way to simplify this? Well, not really. I mean, I could factor out like a 2 theta, but I'm not really sure what that would be worth. So let me move on now to expressing y in terms of theta. So y is going to be r sine of theta. So it's going to be 2 theta squared times the sine of theta. That's another product rule. So again, we have 2 theta squared. This time we have sine of theta. Derivatives are going to be 4 theta again, and now this time it's going to be cosine of theta. Multiplying that out with the ribbon, we've got 4 theta sine of theta plus 2 theta squared cosine of theta. Okay, so let's put all this together now. dy over dx evaluated at theta equals pi, that's going to be y prime of pi over x prime of pi. Just using our parametric derivative setup here. So let's see, that's going to be 4 pi sine pi plus 2 pi squared cosine of pi. That's all in the numerator. Denominator, we've got 4 pi cosine of pi minus 2 pi squared sine of pi. All that stuff. But now I have to evaluate all this to get one of the answer choices. So here we got sine of theta, which sine of 180 I know is going to be 0 because that's the y value at 180 on the unit circle. So this first term is just gone. For this next term here, cosine of theta, that's negative 1. So this ends up being negative 2 pi squared. Downstairs now, again, cosine of pi is negative 1, so this is negative 4 pi. And then over here, sine of theta is 0, or sine of pi is 0, so this term gets zeroed out. So we have minus 4 pi down there. And reducing this, this is going to be 1 over 2 pi on top, so pi over 2. When all is said and done, we get answer choice B. For this problem, we have this function, theta cubed minus 6 theta squared plus 9 theta, that is always non-negative for at least all thetas that are greater than or equal to 0. And they're telling us during the time interval we have a particle moving along the polar curve, which is basically r is just this f function here, so that at every time we've got theta and time being the same thing. Okay, so we want to know on what intervals of time, in other words, what theta values, is the distance between our particle and the origin increasing. So the key here is recognizing that r with these polar curves is your distance from the origin. So that means our distance is going to be increasing where the r and the r prime, the change in distance, have the same sign. If we have a positive r and a positive r prime, that means that our particle is to the positive direction of the origin and also moving further away. If they're both negative, then it's moving backwards, but again, further away. So we have to figure out where they have the same sign. Now, part of the key on this is this f of theta greater than or equal to 0 they said in the beginning. They're basically saying that r is always non-negative. What that means is we just have to figure out where r prime, in other words, f prime, is non-negative, greater than or equal to 0. So to do that, we're going to have to find critical values and do a little sign analysis. F prime of theta then, that's going to be 3 theta squared, just using our power rule here, minus 12 theta plus 9, and we want to see what that equals 0. This is a no calculator problem, so I'm just going to do this the old-fashioned way. I can start by factoring a 3 out of here. So that's going to be theta squared minus 4 theta plus 3. All that equals 0. And let's see, things that multiply to 3 and add up to negative 4. That's negative 1 and negative 3. So that means that theta has values of 1 or 3. Now, both of these are in the interval from 0 to 2 pi, so we have to consider both of these critical values. Let's do some sign analysis now. So I've got a number line I'm whipping out here. This is the f prime line. And I've got my endpoints, first of all, 0 and 2 pi. I want to make sure to make this legitimate that I don't try testing anything to the left or the right of those. And then my critical values 1 and 3. Going through now and testing a few values, let's pick something between 0 and 1, like 1/2. So that's going to be a negative times a negative is a positive. And then something between 1 and 3, like 2. That's going to be a positive times a negative, so negative. And this is going to be a little trickier, something between 3 and 2 pi. Well, maybe you don't know exactly what 2 pi is, but you know pi is about 3.14. So this is a little bit more than 6. So I'm going to pick a number like 4 that's definitely between those. So that's going to be positive, positive, all comes out positive. So we see here that f prime is positive, and just because it's positive everywhere, f of 0 is greater than or equal to 0 on the intervals from 0 to 1 and also 3 to 2 pi. That means that our distance will be increasing on those intervals, which matches up with answer choice D. For this problem part, they want expressions for dx over d theta and dy over d theta. So basically x prime of theta and y prime of theta. We'll start with the idea that the x value equals r times the cosine of theta. So that's going to be 1 minus 2 cosine of theta in the parentheses times cosine of theta. This first piece is r. This is just a cosine that's always there when you're finding x values. All right, well, let's distribute this out and see if we can simplify it a little bit before we take any derivatives. So we'll have cosine, and this will be minus 2 cosine squared of theta. And taking some derivatives now, we have negative sine of theta minus, this will be 4 cosine of theta times negative sine of theta. So that's actually going to be positive because we have a negative out here that would have been there, but it turned positive because of the negative from this sine term here. Okay, so moving on then. This second term, actually, we can simplify that a little bit. We know that 2 cosine sine is equivalent to sine of 2 theta. So this is going to be 2 sine of 2 theta. Now we're going to move on to y prime. We've already got x prime. It's as simple as it's going to get. Y prime is going to be our radius, 1 minus 2 cosine of theta times sine of theta. And multiplying that out now, we've got sine of theta minus 2 sine of theta cosine of theta. Now we know this term here, 2 cosine sine, that's really sine of 2 theta. So we can simplify that as well. And let's see here. Now we actually need to take a derivative. We haven't taken a derivative yet. I got a little turned around because we used that double angle identity on the derivative of x, but we haven't even done that on y yet, and we still need to use the identity. So taking the derivative, we've got cosine of theta, and this is going to be minus 2 cosine of 2 theta. Pretty straightforward chain rule there. And we're done with this part of the problem. On this problem, they want an equation in terms of x and y for the tangent line for a polar curve at the point where theta equals pi over 2. So we basically need an x, a y, and a dy over dx. To get all those things to help us with those, I displayed the stuff we already found from the earlier problem there. This was from part B. So we had x and x prime of theta, y and y prime of theta. Here we go. Now these first two are actually going to be pretty useful trying to find x and y for this equation here. We can write x equals cosine of pi over 2 minus 2 cosine squared of pi over 2. So this is going to be, let's see here, this is 0. Cosine of pi over 2 is 0. Squaring that still gives me 0. So all this gets zeroed out. So that's the x value then. And then for our tangent line. And then we've got, let's see, y of pi over 2, that's going to be sine of pi over 2 minus sine of 2 pi over 2. Well, sine of pi over 2 is just 1. This over here is really sine of pi, which is 0. So 1 when the dust settles. Next, let's get the derivative. For that, we need y prime of pi over 2 over x prime of pi over 2, just using our parametric setup here. So let's see, y prime, that's going to be cosine of pi over 2 minus 2 cosine 2 times pi over 2, all that stuff. For x prime, we've got negative sine of pi over 2 plus 2 sine of 2 pi over 2. And then simplifying things a little bit, although we don't actually have to at this point because this is all constants, but just for the sake of practice here, we've got cosine of pi over 2 is 0. This is really cosine of pi, which is negative 1, times negative 2 gives us positive 2. Downstairs, we've got sine of pi, which is 0, negative sine of pi over 2, that's going to be negative 1. So negative 2 when the dust settles. But wait, we're not done. We actually need to write the equation of the tangent line. So we've got y minus the y value 1 equals our slope we just found of negative 2 times x minus our x value of 0. And there's our final answer. For this part of the problem, between 0 and 3 pi over 2, they want the greatest distance from any point on the graph of R here to the origin, and then justify the answer. So this is basically an absolute max min kind of problem. We want to find the greater of the absolute max and absolute min for basically the R function. R is telling us how far we are from the origin. So we just need to maximize or minimize R, and you know, whichever one is further away in terms of absolute value, that's going to be our answer for this problem. So to do this, let me get some critical values. For that, I'm going to need R prime, which they actually already gave us here. So let me just set that equal to 0. There's no way to make it undefined, so it's 0 or nothing for those critical values. So setting that equal to 0, I actually am going to do that on the graphing calculator. Now, I stored R prime as y2 in my graphing calculator. And in order to do this, I do need to use function rather than polar mode. So going to the calculator here. I'm here in my y equals. On the last part of the problem, I used the original function and found the intercepts. I'm going to deselect that now, and I'm going to select the derivative that I wrote in y2. And I've still got the same window from 0 to 3 pi over 2. So I can just do zoom 0, and it should give me exactly the window I need to figure this out. So there's my R prime from 0 to 3 pi over 2. And we're just going to find these two intersection points here. Those will be our critical values. So second trace and option for 0, so option 2. And let me move my spider a little bit to the left of this intersection and a little bit to the right of that x-intercept, and enter. So that's about 0.8603. That probably equates to something with pi's in it, but we're allowed to use a calculator, so I'm just going to round it off. And I'm actually, so that's that value. I'm going to call that A, and I'm going to store that on my calculator before I find the other x-intercept. So quitting out of there, let me just store that as alpha A. All right, going back to my graph now, let me do second trace option 2 again for zeros. And now let me find that other x-intercept. So moving my spider along, and you could just enter x values directly, but I like to see where I am here. So enter once to the left, enter once to the right, enter one more time. We've got this other number, 3.4256 and some change. I'm going to store that as B on my calculator. So quit out of there and stow alpha B. So now I can use those whenever I want. At this point now, I have to run my candidates test. I have two critical values here, so I can't just say, we have one critical value and this is it. So let me do the endpoints and these two critical values plugged into the R function, which I can do on the calculator. Now, I don't really need the calculator to do R of 0 and R of 3 pi over 2, because that's the beginning and the ending of this function, which we saw earlier. It begins and ends at the pole. So those both have a distance of 0 from the origin. So these equal each other, and they both equal 0. But we have to show that because we're doing the candidates test here. Now let me figure out R of A. So on my calculator, since I stored R as y1, I'm just doing y1, open a parentheses, and plugging that A constant in there to get about 0.5611 and some change. Okay, we'll take their word for it. Let me now find R of B, the other constant, the other critical value. So let me just go and get my input from before and press enter to steal that. And then let me just replace the A with alpha B. This is why I stored these, to make this part easier. That's about negative 3.288. Now, taking a look at all of these, the furthest one away from the origin, the biggest overall absolute distance, is going to be what B returned here, this negative 3.288. So I'm going to say the greatest distance is just the absolute value of that, which is, and we have to spell this out, is positive 3.288. For this last part of the problem, they're telling us there's a point on the curve at which the slope of the line tangent to the curve is 2 over 2 minus pi. At this point, we're told dy over d theta, in other words, y prime of theta, is 1/2. They want x prime of theta, dx over d theta. So in general, we have to remember that polar slope has the setup of basically y prime of theta over x prime of theta. You have to do it parametrically. You can't just use r the way it is. So we've got, let's see here, dy over dx equals dy over d theta over dx over d theta. This is y prime over x prime. Now here we don't actually have to express anything parametrically and do that dance, because they told us what dy over d theta is. They also told us that the overall dy over dx, the slope, was 2 over 2 minus pi. So we can set up just a little equation using this right here. Instead of dy over dx, I'm just going to write 2 over 2 minus pi. And for this big crazy fraction, I've really got 1/2 over dx over d theta. Now I just have to solve for dx over d theta. I'm going to cross multiply here. So I've got 2 dx over d theta on the left side. And on the right side, I've just got all of this stuff times 1/2. So we'll just write 2 minus pi over 2. And now just dividing both sides by 2 to isolate dx over d theta, we have 2 minus pi over 4. And that's going to be good enough to call it an answer.